Hello and welcome to our Home of Coatings webinar studio. Our moderator, Marco Samland, is still in makeup. We'll get started right away. Hot or cold drink ready. We want you to have a good time at our live event. Our experts are looking forward to it. Are you ready? Let's go.
So, ladies and gentlemen, here we are. A very warm welcome to today's webinar. My name is Marco Samland and I'm excited to be your host and moderator. You've made the right choice by taking the time to be here, and we are thrilled to have you with us. Feel free to make yourself comfortable as possible, so grab a coffee, tea, or your favorite drink, sit back, relax, and enjoy the session. We want you to feel at home here. We're excited to dive into today's topic together. Don't hesitate to ask questions and actively participate in our live polls, 2 in total. Incoming questions will be posted again. This is simply due to the conference tool GoToWebinar. And today, the webinar is taking place in close collaboration with our dear colleagues from Oil Additives. The webinar is titled Precision, Performance, Possibilities, VISIOMER Specialty Methacrylates for 3D Printing. The short trailer at the very beginning was played on our Coutinho campus, the exceptional knowledge and information platform for the coatings and the inks industry. It's the one-stop hub where all past and upcoming webinars, presentations, e-learning modules, a coating glossary, and so much more wow in know-how are available 24/7 on demand, free of charge. Our experts for today are full of anticipation and can hardly wait to get started. So let me welcome them to our digital webinar stage. A warm welcome to Sabine Kömmelt, Global Marketing Specialty Methacrylates, and Adnan Khalil, Lab Manager Applied Technology in Specialty Methacrylates. Good morning, Sabine and Adnan, and I can see you.
Hi, Marco.
Good morning, Marco.
And I can hear you. Perfect. And now, Adnan, you have the permission to share the final slides with us. Hopefully, you're in good mood and
okay, great mood.
Great mood. And we can see this the presentation, so the digital stage is yours. Go ahead, please.
Okay, just checking the laser pointer. Yes, thank you, Marco, again for the very kind and energetic introduction, and of course also a warm welcome to everybody from my side, and a big thank you for participating in our today's webinar, which is addressing VISIOMER Specialty Methacrylates for 3D printing resins. As mentioned also by Marco, my name is Adnan Khalil, and I'm part of the Evonik Specialty Methacrylates team, and I'm currently working as a lab manager in the Applied Technology department here. And today I would like to discuss how our VISIOMER Specialty Methacrylates can contribute to the development of next generation photopolymer resins for 3D printing, with a particular focus on wet photopolymerization technologies. Maybe before we dive into the chemistry, let me briefly introduce our Evonik Specialty Methacrylates business. So we have been developing and manufacturing specialty methacrylates for more than 80 years now, and have supported customers across a wide range of applications, like different coatings applications, different adhesive systems, composites, and many more. And beyond supplying products, we closely work with our customers to develop tailored solutions, provide scale-up support, and help bring innovations basically from the lab scale to commercial production. And as mentioned, many applications fields rely on our specialty methacrylates, with the additive manufacturing or the 3D printing being one of them, and our focus for today's session. Maybe briefly as an introduction, so what is additive manufacturing or 3D printing? So in general, it consists of different process categories, with each building three-dimensional objects, but using fundamentally different mechanisms and materials. So for example, probably the most common technology, the material extrusions technology, such as FDM, where typically thermoplastic filaments are deposited by melting through a nozzle, and is widely used for rather rapid prototyping and cost-effective manufacturing. Then also powder bed fusion technologies, including SLS and SLM, that use polymer or metal powders that are selectively fused by a laser or an electron beam, enabling the production of really highly complex and mechanically robust parts. Material jetting and binder jetting, they rely on entirely different material concepts, I would say, with the deposition of a liquid binder onto a powder bed. And our focus today is, as I mentioned in the beginning, the wet photopolymerization, which includes SLA and DLP technologies. And these technologies use liquid reactive resin systems that are selectively cured by a light source. And they are particularly attractive because they offer really high resolution, good surface quality. You can produce really fine features with it in a reproducible manner. And it is based on a broad formulation flexibility. And these advantages have made the photopolymerization a key technologies for different applications, ranging from prototyping to dental devices to rather advanced engineering and specialty materials. And to understand where monomers, so our specialty methacrylates, fit into the picture, I would like to have a brief look at how these resins are typically structured and how the process is working. So in general, in a wet photopolymerization, liquid resin is selectively exposed to light and converted into a three-dimensional solid structure in a layer by layer manner. The resin itself is typically composed of 4 major building blocks. So we have oligomers that provide the primary mechanical backbone. Then we have reactive diluents, which can be monofunctional monomers or multifunctional crosslinkers that can control the viscosity and of course also participate in the network formation. We have photoinitiators that basically convert the light energy into reactive species that initiates a polymerization. And finally, we have additives that can contribute to color, stability, processing behavior, or a specific functionality. And through the controlled curing and network formation, the liquid resins are then transformed into highly cross-linked materials, which has tailored properties for different 3D printing and applications. And as I mentioned, this process enables the production of highly detailed part with very good surface quality and the dimensional accuracy. And as the final performance of the resin is strongly governed by the choice of reactive diluents, so monofunctional methacrylates and also multifunctional methacrylates, that's exactly why specialty methacrylate can play an important role here. But before looking at individual molecules, I would like to briefly discuss with you what we believe a modern resin formulation needs to achieve. So from our perspective, the resin development is rarely about optimizing a single property. Instead, there are multiple requirements often competing requirements that need to be balanced. So, for example, the resin has to process well, it should have an acceptable viscosity, also acceptable handling in terms of safety. It has to have an effective curing speed. At the same time, the final part must provide sufficient mechanical properties such as stiffness, toughness, durability, and thermal stability, which can always differ depending on the end application. Then, in addition, the market expectations also continue to evolve. So increasingly, formulators are looking for lower hazard classification, reduced odor, low VOC content, increased content of renewable material, and therefore improved sustainability. One of the more challenging but also interesting trends in the industry is trying to combine high HDT value, so the heat deflection temperature, which describes the deformation upon applying a pressure at a specific temperature, and to combine it with a high toughness property. And traditionally, these two properties, they tend to work against each other. So therefore, the resin development today is really about balancing, like I mentioned, processability, performance, sustainability, and safety. And to address these diverse requirements, we as Specialty Methacrylates from Evonik, we offer a broad portfolio of different specialty methacrylates. So we offer a very versatile toolbox to address these different challenges in this application, but also in a wide field of different applications, with the 3D printing just being one of them. Please do not be confused by all of these abbreviations. Right now, I will try to clarify the important ones for today in more detail in the following. But in general, our portfolio can be clustered into different groups based on different chemistries, such as alkyl and aryl methacrylates. We have multifunctional crosslinkers or more special monomers with, for example, ether or acetal functionalities, with amino functionalities, or phosphate groups, for example. You will also find monomers that are marked by a leaf. That means they are made from raw materials with a biocarbon content, as well as products that are labeled as a Terra product, for example, the Terra C13MA and the Terra C74MA, which means they contain a biocarbon content and are also friendly in labeling. And with this broader portfolio, this allows us to support many polymer technologies. But for today's webinar, I would like to concentrate on a few selected products that are particularly relevant for reactive resin systems in photopolymer applications. So let's first start with the monofunctional methacrylates. So our monofunctional methacrylates, they allow formulators to fine-tune different properties such as the TG or the hydrophilicity / hydrophobicity, viscosity, flexibility, as well as thermal performance indicated by the TG values in each box here. So in general, this figure indicates how different VISIOMER monomers occupy different positions in this property space. For example, the VISIOMER portfolio contains a variety of long-chain alkyl methacrylates that can be used to adjust the hardness or softness of the final polymer. Typically, the longer the alkyl side chain, the lower the glass transition temperature of the final polymer, and the more flexible is the resulting material. Here we offer also different type of alkyl or long chain alkyl methacrylates that can differ in branching, like the EHMA and the IDMA, or in chain lengths like the Terra C13MA and the Terra C74MA. And such unpolar hydrophobic components can also improve moisture resistance in the end application, oxidative resistance, as well as it can improve adhesion to unpolar surfaces. Furthermore, our portfolio also contains more cyclic aryl and alkyl methacrylates with rather more bulky side chains and higher TG values, which can be used to increase the hardness or the mechanical properties of the final polymer. For example, the Terra Iboma has the highest TG of our portfolio with about 150 degrees Celsius. Besides these rather hydrophobic monomers, we also offer ether and acetal methacrylates that are relatively more hydrophilic and provide functional groups for increasing, for example, molecular interactions. A very popular cyclic ether monomer, especially used in methacrylic-based reactive adhesive systems and 3D printing resins, is the THFMA, which can provide good solvency for different oligomer and polymer components. It has a rather low shrinkage and shows good adhesion to a variety of different surfaces, while also having a really low odor. However, as in recent years, the hazardous labeling has become more and more relevant. The application of the THFMA has become more restricted because it is labeled as a CMR substance, as you can see here. One of our newer monomer, the Terra IPGMAs, can be a great alternative, as in specific applications it can show similar or even better properties while being more label friendly and nearly odorless. And this aspect is also highlighted in this slide. So in 3D printing, to us, the labeling, of course, is also a significant factor. So many of today's commonly used reactive diluents, they provide really excellent performance. Examples include the ACMO, the THFA, so the acrylate version of the THFMA, the CTPFA, or the FEMA. So despite their excellent performance, these materials often carry a significant hazard classification, and as a result, many formulators are now asking for more label-friendly alternatives. And this is exactly where selected VISIOMER products can provide value. So products such as the Terra IPGMA, the Terra Iboma, or the Terra BNMA can offer opportunities to improve the formulation safety while also maintaining functionality, which already brings us to our first poll.
Yes, correct, Adnan. So let's start the first poll. In total, we have 2, and I would like to share the first one. So here we are, the audience. The question is, how important is labeling to you? Feel free to click. And as I always say, also to drink something, but please click. And after a while, we would like to share the final results to our experts and we'll then continue. But first now, it's up to you, the audience. Ladies and gentlemen, yes, 5% voted. Now we have 21, 37% voted. Over 40% voted. Always good to see, to have an actively audience. Yeah, 53%. Mm-hmm. 55, 60, 65. So let's wait some more seconds. Should be clear, but let's wait. 65, 65, and I will start my final last countdown for the first polling. So 5, 4, 3, 2, 2, 1, and let's share the results. First of all, many thanks to all of you. Here we are. Hopefully, Adnan, you can see them.
Yes, I can see it.
Perfect. So it's clear, I think.
Yeah, it's a really clear picture. That's really good. Yeah, that's really good for us. I hope that this shows that we are on the right track with our specialty monomers.
Okay, then back in game, back for you,
Okay.
and continue, please.
Okay. Thank you for all for participating in this poll. This is rather positive for us because this gives us a chance also again to highlight one of our newer products, the VISIOMER IPGMA, because this is a nearly odorless methacrylate that is especially designed for formulators that are seeking safer and more sustainable reactive diluent solutions. So the Terra IPGMA has a bio-based carbon content of around 30%, so it supports sustainability initiatives while maintaining the processing advantages as expected from a modern reactive diluent monomer. It has a rather balanced polarity, which enables it to be used in a broad formulation compatibility, making it suitable especially for methacrylic reactive systems, for example, for structural adhesives or photopolymer resins. It has a really low odor, which stems from its very low vapor pressure, as illustrated here on the right-hand side. So compared with the conventional monomers, such as the MMA, the methyl methacrylate, significantly less material enters the gas phase during processing, which contributes to its reduced odor perception and a more comfortable working environment. So in terms of sustainability, odor, and safety perspective, the IPGMA has several benefits, but also during application in the 3D printing resin, the IPGMA can bring technical advantages. To investigate this, we benchmarked the Terra IPGMA against the commonly used hydrofunctional methacrylates in a representative photopolymer formulation, and we found that the Terra IPGMA can be readily incorporated into a typical photopolymer resin formulation while maintaining good key mechanical properties that are required for the 3D printing application. So when comparing the Terra IPGMA with the HEMA in the same formulation, the resulting cured material properties, they exhibit very similar tensile strength and E-modulus, elongation at break, and heat deflection temperature. So again, in other words, the substitution of the HEMA by the Terra IPGMA can be achieved without sacrificing the overall mechanical performance of the printed part. And beyond the mechanical performance, the Terra IPGMA also provides a significant advantage in terms of water uptake behavior. So as shown here on the left, the formulation containing the Terra IPGMA absorbs substantially less water over time compared to the corresponding HEMA system. And the reduced water adsorption can contribute to improved dimensional stability, better retention of mechanical properties under humid conditions, and an enhanced long-term durability of the printed components. Next, I would like to have a closer look at another monofunctional monomer of our portfolio. This is the VISIOMER Terra Iboma. The Terra Iboma is, as I also mentioned in the beginning, a high TG methacrylate with approximately 72% biocarbon content and TG value of around 150 degrees C. So thanks to this rigid isobornyl structure, the Terra Iboma is highly effective in increasing stiffness, dimensional stability, and heat resistance in photopolymer networks. To demonstrate this effect of the Terra Iboma in a photopolymer formulation, we compared different ratios of the TerraIBOMA and TerraIPGMA as a reactive diluent, while keeping the remaining resin composition in the photopolymer formulation constant. So what can be observed here on the left is very clearly that increasing the TerraIBOMA content, this leads to an improvement in the thermal performance, in this case indicated by the heat deflection temperature. So as the proportion of the IBOMA increases from 1 to 2 ratio to a 2 to 1 ratio, the heat deflection temperature increases significantly. At the same time, we do not observe a trade-off in mechanical properties. In fact, we see also that the tensile strength increases with the increasing IBOMA content, because the final TG of the polymer also increases. So this demonstrates also an important principle. So by adjusting the ratio of the TerraIBOMA and the TerraIPGMA, formulators can tailor the balance between not only the handling properties and the sustainability benefits, but also with the thermal mechanical performance. So in this specific case, the TerraIPGMA and TerraIBOMA can be viewed as complementary building blocks that allow resin designers to tune their performance according to the application requirements. Okay, so up to this point, we've focused primarily on the monofunctional methacrylates, using the TerraIPGMA and the TerraIBOMA as examples of how reactive diluents can influence key properties such as viscosity, moisture resistance, and thermal performance in combination with sustainability benefits. But the ultimate performance of the printed part is largely determined by the cross-linked network that is formed during the curing. That means that achieving the desired balance of specific mechanical properties such as toughness, flexibility, HDT, as well as chemical resistance, this requires also a careful selection of a cross-linking component. And this slide provides an overview of the VISIOMER crosslinkers in our portfolio and illustrates how different crosslinkers can be used to tailor resin properties through their molecular structure, their polarity, their viscosity, and of course their functionality. So in general, the portfolio covers a broad range of chemistries, ranging also from relatively flexible crosslinkers such as the HEMA-TMDI to rather more highly rigid structures such as the TMP-TMA and the Terra-ISDMA. This again allows the formulators to tune the balance between flexibility and stiffness according to the targeted end application. At the same time, the portfolio also spans a wide again, hydrophobicity and hydrophilicity range. So more hydrophobic crosslinkers can support moisture resistance, dimensional stability, whereas more hydrophilic structures may improve the compatibility with other polar formulation components. Another aspect, important aspect, is the viscosity, as shown again by the color coding. So the products cover a broad viscosity range, enabling the formulators to optimize their processing while remaining the desired level of crosslinking. For example, the 1,6 HDDMA or the BDDMAs and the EGDMA, they are widely used rather low viscosity crosslinkers for an efficient network formation. The PEG 200 DMA and the TRG DMA, they have a more flexible and hydrophilic character, and the TMP TMA delivers high crosslinking density and due to its dry functionality, and the ISDMA combines a high rigid cyclic structure with a favorable sustainability profile. One of the crosslinkers that maybe deserves special attention is the HEMA-TMDI. So unlike many traditional dimethacrylates, the HEMA-TMDI contains a relatively flexible linkage that combines the polymerizable methacrylate groups with urethane functions. And due to the effective hydrogen bonding of the urethane functionality, this promotes a good compatibility with urethane methacrylic or acrylic oligomers, which are among the most widely used oligomer classes in high performance SLA and DLP resins. So as a result, it is frequently used in 3D printing resins when a formulation requires a really balance between crosslink density and tough material properties. So on this slide, we wanted to demonstrate how this key crosslinker, the VISIOMER HEMA-TMDI, compares against some of the most widely established benchmark materials in UV curable or photopolymer resin formulations, namely the BISGMA and the EBITDA type crosslinker, so ethoxylated, bisphenol A methacrylate crosslinker and agents. And the comparison demonstrates that the HEMA-TMDI offers a highly attractive balance between processability and the final part performance. So looking first at the viscosity, the formulation containing the HEMA-TMDI sits in between the two different materials, while it exhibits somewhat higher viscosity than the EBITDA. In this case, it remains significantly easier to process than the highly viscous BISGMA system. More importantly, this good processability is also achieved without compromising the performance. So the cured HEMA-TMDI formulation reaches an HET of around 78 degrees Celsius, matching the performance of the BISGMA and significantly exceeding the performance of the EBITDA reference. Furthermore, the HEMA-TMDI delivers a rather good toughness, as reflected by the ISAT impact strength in this case, and a comparatively high elongation at break. And this behavior is consistent with the urethane containing molecular structure of the HEMA-TMDI. So as I mentioned before, the urethane linkages, they introduce strong intermolecular interactions while also enabling better stress dissipation within the network. So the resulting formulation is less brittle than a highly balanced property profile that and it provides a highly balanced property profile which combines high thermal performance, good toughness, and mechanical strength, as well as manageable formulation viscosity. And this balance is particularly attractive for the engineering of photopolymer application, where both durability and heat resistance are required. And this brings us to our second pole.
Correct. After the one comes the two, same procedure, but it's the last poll for today's webinar. And here we are. Second question. Are you already using methacrylic crosslinkers in your 3D printing resin? So dear audience, please feel free to click, only one click. And after some minutes, no seconds, we will share the final results to all of you. It's the last poll for today. So please, ladies and gentlemen, it's time to start. Perfect. Good to see. 9% voted. Now we are near to the 20%, over 20%. So reaching the 30% now, 30%. 30% up to now. Let's wait. 35. Only one click. Okay, yeah, 3 answer possibilities up to now. So let's wait some more seconds. 41%. But currently, I would say there's one winner to say so. So let's start the final countdown. So 5, 4, 3, 2, 1. And here we are. So Adnan, do you think 44% is no, do not use, and then there's a mix?
Yeah, then I hope we can convince some of the audience today to use more methacrylic crosslinkers, especially the HEMA TMDI. I hope our presentation is kind of persuading in this case.
Okay, we can see the presentation again.
Great, thank you, Marco. So again, thank you for participating in this poll. In this next example, or maybe again in the previous example, we compared the HEMA TMDI against established benchmark materials, namely the BIS GMA and the EBITDA type dimethacrylates, and demonstrated that the HEMA TMDI provides a particularly attractive balance of processability, thermal performance, and toughness. However, urethane-containing crosslinkers represent only one part of the formulation toolbox. So in practice, formulators frequently employ lower viscosity methacrylate crosslinkers to improve the resin handling and the processing. So it is worthwhile to examine how the HEMA TMDI compares against more conventional methacrylate-based crosslinkers, such as the TRG DMA and the PEC 200 DMA. And this slide highlights an important aspect of the resin design, that the crosslinkers influence far more than just the mechanical properties. So looking first at the viscosity, you can see that the TRG DMA and the PEC 200 DMA result in much less viscous material, which can provide an advantage in the processing and make them potentially attractive for highly filled formulations or applications where a really good flow behavior is necessary. However, when we evaluate the properties of the cured material, the picture becomes a little bit more differentiated. So as we also saw previously, the HEMA TMDI delivers a unique combination of mechanical performance and toughness and thermal resistance, while the TRG DMA also delivers a high HET in this comparison. It also exhibits a significantly lower impact resistance. The PEC 200 DMA, on the other hand, provides a better toughness, but at the expense of the thermal performance. And another relevant observation is the curing behavior, which is here indicated by the critical exposure energy. So the minimum light energy that is required to transform the liquid resin into a solid polymer network. And we see that the critical exposure energy is substantially lower for the HEMA TMDI containing formulations than it is for the TRG DMA or the PEC 200 DMA systems. And this demonstrates that changing the crosslinker not only alters the material properties, but also affects the printing process itself. So exposure settings that produce optimum results for one formulation may be completely inadequate for another. And consequently, a successful resin development requires simultaneously optimization of both the formulation and the printing parameters. Which brings me to our last example of today's session. This is another exciting, rather new addition to our portfolio, the Terra ISDMA. So the Terra ISDMA is a low shrinkage, partially bio-based dimethacrylate that is designed for high performance resin systems. It combines the low polymerization shrinkage with a moderate viscosity and has a really rigid molecular structure that is capable of delivering really good thermal performance. And this characteristic make it especially attractive for engineering photopolymer applications. And in this context, we evaluated, or to evaluate this, the Terra ISDMA, we compared it against several rigid benchmark crosslinkers that are commonly used in high temperature photopolymer formulations. And this included this three established crosslinkers that are shown here on the left, which are frequently considered for high temperature resin systems, so the TCDDMA, the TCDDA, and the DOGDA. And all of these materials are known for their ability to increase network rigidity and thermal resistance. And when we applied the Terra ISDMA in the same model formulation, we observed the highest HDT value of all the materials that were investigated, while maintaining also the tensile strength at a comparable level. So at the same time, the ISDMA offers a low shrinkage and a significant renewable carbon content, making it also an attractive solution for, again, for high performance 3D printing resins. And yes, with this, I would like to conclude by trying to briefly summarizing the key messages from today's presentation. I hope that we have seen that methacrylates can offer much more than simply serving as a viscosity reducer in photopolymer formulation. So through targeted molecular design, they provide the formulators with powerful tools to tailor their not only the processing but also the mechanical performance as well as sustainability characteristics. So we started with our specialty mono esters and have demonstrated that our label-friendly Terra IPGMA and Terra IBOMA can contribute to a safer formulation whilst simultaneously addressing important application requirements such as moisture resistance and heat resistance, or heat deflection temperature in this case. And we then expanded the discussion to our cross-linking monomers and showed how different cross-linker architectures can be used to control network formation and the final performance of the printed parts. So depending on the target application, the formulators can choose between solutions that were optimized for toughness, flexibility, low viscosity, high HDT, and low shrinkage. Particularly the examples such as the Hematim DI and the Terra ISDMA highlighted that formulation performance is not only determined by a single property, but rather by balancing processability, curing behavior, mechanical properties, and thermal stability. So with this, I would like to say thank you for your attention. I'm happy to discuss any questions now or later. You can also use our digital contact information to contact my colleague Sabine or me anytime. And yes, I'm open for discussion. Thank you.
That's always a good point. And first of all, welcome also Sabine Kömmelt. And Adnan, first of all, many thanks for the insights, for the presentation. And there are currently 3 questions in my inbox. We copy and pasted them. So the audience, feel free. If you have any questions, it's time now for every question. And let's start with the first one. And you can answer as good as possible. If you need more, sometimes more information, no problem. Yeah, afterwards you will get the report, no problem. So the first one, how do the curing conditions influence the final properties?
Yeah, so this is important questions because in photopolymer resins, the final properties are not solely determined by the formulation. They are determined by the combination of the curing properties and the formulation chemistry. So the curing conditions, they can influence how quickly a network forms, how many double bonds are converted, how homogeneous the cross-linking structure in the end becomes, and how much stress remains, for example, in the printed part. So in general, maybe one can say that a too low energy input results in a not fully cured final system that leads to a lower mechanical property, and a too high energy input can lead to an overcuring of the material, which can lead to warpage, microcracks, and inaccuracies that later heavily influence the final properties.
Many thanks. The second one, which monomer would you recommend for a high impact resin?
So in general, okay, so from the materials we presented today, and if we are focusing solely maybe or want to highlight one monomer, I would recommend starting with the HEMA TMDI. So this is probably the most attractive starting point because, as I mentioned also in the presentation, the urethane functionality, it contributes significantly to the toughness and impact resistance while maintaining the good thermal performance. But I also want to maybe highlight that a high impact performance is usually not achieved by just a single monomer, but rather through the combination of the monomer with the oligomer, which is also, of course, an important component in the final formulation, as well as, again, the optimized curing conditions are also important.
And currently the last one, but also a good one, I would say. Where can I order samples of your products?
Yeah, so samples, I think the easiest way is to directly contact my colleague Sabine and myself, and then we can figure out the rest. But for all of the structures that were shown in the presentation, samples are readily available.
Perfect. So as I did use your mobile phone, yeah, it's working, but also contact them via everything you would like on LinkedIn or the official email address or whatever. Yeah, perfect.
Yes.
So let's check, because we have also to check currently, is there any in our inbox? Currently, there are no further questions, but feel free. Of course, we will not wait 11 minutes. Yeah, so the audience, if you have any questions, it's now time for you. There will be also, I would say, 6 hours later, the second session. Yeah. So if you missed this one or you have colleagues around the world, there's also the possibility to join later. Second session, as I said, but let's have a look again. But if there are no further questions, I would, of course, hand over again to you, Adnan, for your final last words to our audience. And then I will share my final slides and we'll close this session with a short video. But first of all, Adnan, Khalil, please.
Okay, then I just simply want to say thank you for attending today's webinar. I hope we sparked some interest. As mentioned, please feel free to contact us via the shared digital information. We are happy to always receive some feedback as well. So yeah, thank you. And hopefully until the next time.
Anything to comment from you, Sabine? Or
No, also thank you for your attention. And as Adnan said, there are several channels. You can also use our website or the Contino campus to order samples. So feel free to contact us.
perfect. Then, as Sabine said, you're invited to explore the Contino and also the Contino campus. So please visit contino.com and or contino.com/campus. And then we are now heading into our summer break, dear audience, but we already have many webinars lined up starting in September. All webinars are recorded and can be accessed 24/7, as I said in the morning, meaning you can take advantage of quiet moments to catch up on a missed webinar, perhaps with a fitting drink, iced coffee or whatever in your head. So with the final last video, as I said, I leave you with our mutual best wishes. See you next time. Have a nice vacation or a nice working time during this time, summertime or whatever. See you in the next webinar. And that's it for today's webinar. I will close now the camera also to you, dear colleagues, Sabine, Adnan, and I will share the final last video, and all the best to you all.
We hope you liked today's live event. Please visit cotino.com/campus to view the recording and download the handout. And there is a lot more to explore and learn on Contino campus. 24/7 available. Free of charge. For newcomers and experts. Find all upcoming live events right on the main page. Our experts share their knowledge. Missed the live event? No problem. Our knowledge is ready for you. All past events at your disposal. Enroll and start your desired recorded event. Of course, the handout can also be downloaded under Resources. Discover the wow and know-how. Discover Contino Campus.